Electrons do not travel at the same speed regardless of the voltage input. In a conductor, electrons move freely due to their thermal energy. When a voltage is applied, it creates an electric field that exerts a force on the electrons, causing them to accelerate and gain kinetic energy. This increased kinetic energy results in higher electron speeds. The relationship between voltage and electron speed is given by the equation Vd equals mu times E, where Vd is the electron drift velocity or speed, mu is the electron mobility, a constant that depends on the material, and E is the electric field strength, which is proportional to the voltage. As the voltage increases, the electric field strength increases, which in turn increases the electron drift velocity. Therefore, electrons travel faster at higher voltages. However, it's important to note firstly that electron speeds vary within a conductor, with some electrons moving faster than others due to random thermal motion, and secondly, the average electron speed is proportional to the voltage, but it is not a constant value. The drift velocity of electrons in a conductor is directly related to the applied voltage and the electric field it generates. When a voltage is applied across a conductor, it establishes an electric field that exerts a force on the free electrons within the material. These electrons, which are already in constant random motion due to their thermal energy, experience an additional force due to the electric field. This force causes the electrons to accelerate, but their motion is quickly interrupted by collisions with the atoms of the conductor. These collisions cause the electrons to lose some of their kinetic energy, slowing them down. However, the electric field continues to exert a force, causing them to accelerate again until the next collision. This process of acceleration and collision repeats continuously, resulting in a net drift of the electrons in the direction of the electric field. The average velocity of this drift is known as the drift velocity. The drift velocity is directly proportional to the electric field strength, which in turn is directly proportional to the applied voltage. Therefore, as the voltage increases, the electric field strength increases, and the drift velocity of the electrons also increases. The relationship between voltage, electric field, and drift velocity can be described by the following equations. Firstly, E equals V divided by L, where E is the electric field strength, V is the applied voltage, and L is the length of the conductor. Secondly, Vd equals mu times E, where Vd is the drift velocity, and mu is the electron mobility, a property of the material that describes how easily electrons can move through it. Combining these equations, we get Vd equals mu times V divided by L. This equation clearly shows that the drift velocity is directly proportional to the applied voltage. It's important to note that the drift velocity is typically very small, on the order of millimeters per second, even for large applied voltages. This is because the electrons experience frequent collisions with the atoms of the conductor, which limit their acceleration. However, even though the drift velocity is small, the current that flows through the conductor is still significant because there are a very large number of free electrons available to carry charge. It is also important to distinguish between drift velocity and electron speed. Electron speed refers to the instantaneous velocity of an individual electron, which is constantly changing due to thermal motion and collisions. Drift velocity, on the other hand, is the average velocity of all the electrons in the conductor, taking into account their random motion and the effect of the electric field. In summary, electrons do not travel at the same speed regardless of voltage input. Higher voltage leads to a stronger electric field, which in turn results in a higher drift velocity for the electrons. The relationship between voltage and drift velocity is linear, meaning that doubling the voltage will double the drift velocity. The electron mobility is a measure of how easily electrons can move through a material under the influence of an electric field. It represents the average drift velocity of an electron per unit of electric field strength. In simpler terms, it tells you how fast electrons will move in a material for a given electric field. A high electron mobility means that electrons can move easily through the material, while a low electron mobility means that they will encounter more resistance. Electron mobility is an important property of materials used in electronic devices, as it affects the speed and efficiency of these devices. For example, materials with high electron mobility are often used in transistors to allow for faster switching speeds. The electromobility of a material depends on a number of factors, including the temperature, the presence of impurities, and the crystal structure of the material. In general, electron mobility decreases with increase in temperature as the increased thermal energy causes more collisions between electrons and atoms. Impurities in a material can also scatter electrons, reducing their mobility. The crystal structure of the material can also affect electron mobility, as electrons can move more easily through some crystal structures than others. Some common materials and their approximate electron mobilities at room temperature are listed. Firstly, for silicon, it is approximately 0.14 square meters per volt second. Secondly, for germanium, it is approximately 0.36 square meters per volt second. Thirdly, for gallium arsenide, it is approximately 0.85 square meters per volt second. Fourthly, for indium antimonide, it is approximately 7.7 square meters per volt second. These values are approximate and can vary depending on the specific conditions. Electron mobility is typically measured in units of square meters per volt second. It can be measured using a variety of techniques, such as the Hall effect measurement. The Hall effect is a phenomenon that occurs when a magnetic field is applied to a current-carrying conductor. The magnetic field exerts a force on the moving electrons, causing them to deflect to one side of the conductor. This deflection creates a voltage difference across the conductor, which is known as the Hall voltage. The Hall voltage is proportional to the magnetic field strength, the current, and the electron mobility. Therefore, by measuring the Hall voltage, the magnetic field strength, and the current, one can determine the electron mobility. The electron mobility is an important parameter in semiconductor physics and device engineering. It is used to characterize the quality of semiconductor materials and to design efficient electronic devices. The concept of electron mobility is also related to the conductivity of a material. The conductivity is a measure of how easily a material conducts electricity. It is directly proportional to the electron mobility and the concentration of free electrons in the material. Therefore, materials with high electron mobility and high electron concentration tend to be good conductors of electricity. The electric field strength is a measure of the force exerted on a charged particle by an electric field. It is defined as the force per unit charge. In simpler terms, it tells you how strong the electric field is at a particular point in space. High electric field strength means that a strong force will be exerted on a charged particle, while a low electric field strength means that the force will be weaker. The electric field strength is a vector quantity, meaning that it has both magnitude and direction. The direction of the electric field is the direction of the force that would be exerted on a positive charge. The electric field strength is typically measured in units of volts per meter. It can be calculated using a variety of methods, depending on the situation. For example, the electric field strength between two parallel plates is equal to the voltage difference between the plates divided by the distance between the plates. The electric field strength around a point charge is equal to Coulomb's constant times the charge divided by the square of the distance from the charge. The electric field strength is an important concept in electromagnetism. It is used to describe the behavior of electric charges and fields. It is also used in the design of electronic devices, such as capacitors and transistors. The electric field strength is related to the electric potential, which is a measure of the potential energy of a charged particle in an electric field. The electric field strength is equal to the negative gradient of the electric potential. In other words, the electric field strength points in the direction of the steepest decrease in electric potential. The electric field strength can be used to calculate the force on a charged particle. The force is equal to the charge times the electric field strength. This force is known as the electrostatic force. The electrostatic force is one of the four fundamental forces of nature. It is responsible for the interactions between electric charges. The electric field strength is also related to the electric flux density, which is a measure of the amount of electric field passing through a given area. The electric flux density is equal to the electric field strength times the permittivity of the material. The permittivity of a material is a measure of how easily it can be polarized by an electric field. In summary, The electric field strength is a fundamental concept in electromagnetism. It is a measure of the force exerted on a charged particle by an electric field. It is used to describe the behavior of electric charges and fields, and it is used in the design of electronic devices. The electric field strength is related to the electric potential, the electrostatic force, and the electric flux density. The relationship between voltage and electron speed in a conductor is more complex than a simple linear proportion. Firstly, the drift velocity of electrons, which is the average velocity of electrons due to the electric field, is proportional to the electric field strength, not directly to the voltage. The electric field strength is related to the voltage by the equation E equals V divided by L, where V is the voltage and L is the length of the conductor. Secondly, the electron mobility, which is the proportionality constant between the drift velocity and the electric field strength, is not a constant value. It depends on various factors such as temperature, impurity concentration, and the material properties of the conductor. Thirdly, the electron speed is not uniform throughout the conductor. Electrons are constantly colliding with atoms and other electrons, which causes them to change direction and speed. The drift velocity is just the average velocity of all the electrons in the conductor. Fourthly, the relationship between voltage and electron speed is also affected by the skin effect at high frequencies. The skin effect is the tendency of alternating current to flow near the surface of a conductor, which reduces the effective cross-sectional area of the conductor and increases the resistance. This effect can cause the electron speed to be higher near the surface of the conductor than in the center. Fifthly, the electron speed is also affected by the presence of magnetic fields. Magnetic fields can exert a force on moving electrons, which can cause them to change direction and speed. In summary, the relationship between voltage and electron speed in a conductor is complex and depends on various factors. The drift velocity of electrons is proportional to the electric field strength, but the electron mobility is not a constant value and depends on various factors. The electron speed is not uniform throughout the conductor and is affected by the skin effect in the presence of magnetic fields. The temperature of a conductor has a significant impact on electron mobility. As the temperature increases, the atoms in the conductor vibrate more vigorously. These vibrations cause the electrons to collide more frequently with the atoms, hindering their movement and reducing their mobility. The relationship between temperature and electron mobility is generally inverse. As the temperature increases, the electron mobility decreases. This is because the increased thermal energy of the atoms leads to more scattering of the electrons. The amount of scattering depends on the type of material. In some materials, such as semiconductors, the electron mobility can decrease significantly with increasing temperature. In other materials, such as metals, the electron mobility is less sensitive to temperature changes. The temperature dependence of electron mobility is an important consideration in the design of electronic devices. For example, transistors are often used in high-temperature environments such as automotive engines. In these applications, it is important to use materials that have a high electron mobility at high temperatures. The effect of temperature on electron mobility can be described by the following equation: mu equals mu0 times T to the power of negative n, where mu is the electron mobility at temperature T, mu0 is the electron mobility at a reference temperature, and n is a material-dependent constant. The value of n is typically between 1.5 and 3.0. This equation shows that the electron mobility decreases as the temperature increases. The rate of decrease depends on the value of n. In addition to the effect on electron mobility, temperature can also affect the conductivity of a conductor. The conductivity is proportional to the electron mobility and the electron concentration. As the temperature increases, the electron mobility decreases, which reduces the conductivity. However, the electron concentration can also increase with temperature, which can increase the conductivity. The net effect of temperature on conductivity depends on the material. In some materials, such as semiconductors, the conductivity increases with temperature. In other materials, such as metals, the conductivity decreases with temperature. The presence of impurities in a conductor can significantly affect electron mobility. Impurities are foreign atoms or molecules that are present in the conductor material. These impurities can scatter electrons, reducing their mobility and increasing the resistance of the conductor. The effect of impurities on electron mobility depends on several factors, including the type of impurity, the concentration of impurity, and the temperature. Some impurities are more effective at scattering electrons than others. For example, impurities with a different charge than the host atoms can create strong electric fields that scatter electrons. The concentration of impurities also affects electron mobility. As the concentration of impurities increases, the number of scattering events also increases, reducing the electron mobility. Temperature also affects the scattering of electrons by impurities. At higher temperatures, the electrons have more thermal energy and are more likely to be scattered by impurities. The effect of impurities on electron mobility can be described by Matheson's rule, which states that the total resistivity of a conductor is equal to the sum of the resistivities due to different scattering mechanisms, including scattering by impurities, scattering by phonons or lattice vibrations, and scattering by grain boundaries. The resistivity due to impurity scattering is proportional to the concentration of impurities. Therefore, as the concentration of impurities increases, the resistivity due to impurity scattering also increases, reducing the electron mobility. In summary, impurities in a conductor can significantly reduce electron mobility by scattering electrons. The effect of impurities depends on the type of impurity, the concentration of impurity, and the temperature. The skin effect is a phenomenon that occurs in conductors carrying alternating current. It refers to the tendency of the current to flow primarily near the surface or skin of the conductor, rather than being uniformly distributed throughout its cross-section. This effect becomes more pronounced as the frequency of the alternating current increases. The reason for the skin effect lies in the interaction between the alternating current and the magnetic field it produces. As the alternating current flows through the conductor, it generates a time-varying magnetic field around it. This magnetic field, in turn, induces eddy currents within the conductor. The eddy currents flow in closed loops and oppose the flow of the main current, particularly in the center of the conductor. As a result, the current density is higher near the surface, where the opposing effect of the eddy currents is weaker. The depth to which the alternating current penetrates into the conductor is known as the skin depth, denoted by the symbol delta. The skin depth is inversely proportional to the square root of the frequency of the alternating current, the permeability of the conductor, and the conductivity of the conductor. Mathematically, the skin depth can be expressed as delta equals the square root of 2 divided by omega times mu times sigma, where omega is the angular frequency of the alternating current, mu is the permeability of the conductor, and sigma is the conductivity of the conductor. The skin effect has several important implications. Firstly, it increases the effective resistance of the conductor at high frequencies. Since the current is concentrated near the surface, the cross-sectional area available for current flow is reduced, leading to a higher resistance. Secondly, it can cause power loss in the conductor due to the increased resistance. This power loss is known as skin effect loss and is proportional to the square of the current and the resistance. Thirdly, it can affect the performance of electronic circuits and devices that operate at high frequencies. For example, in transmission lines, the skin effect can cause signal attenuation and distortion. To minimize the skin effect, conductors can be designed with a large surface area or made of materials with high conductivity. Litz wire, which consists of multiple thin strands of insulated wire twisted together, is often used in high-frequency applications to reduce the skin effect. The magnetic field can exert a force on moving electrons, as described by the Lorentz force law. The Lorentz force law states that the force on a charged particle moving in a magnetic field is proportional to the charge of the particle, the velocity of the particle, and the strength of the magnetic field. The direction of the force is perpendicular to both the velocity of the particle and the magnetic field. Mathematically, the Lorentz force can be expressed as F equals Q times V cross B, where F is the force on the charged particle, Q is the charge of the particle, V is the velocity of the particle, and B is the magnetic field. The Lorentz force has several important consequences for the behavior of electrons and conductors. Firstly, it can cause electrons to move in curved paths. If an electron is moving in a magnetic field, the Lorentz force will cause it to deflect from its straight-line path. The radius of curvature of the electron's path is proportional to its momentum and inversely proportional to the magnetic field strength. Secondly, it can cause electrons to accumulate on the surface of a conductor. If a magnetic field is applied to a conductor, the Lorentz force will cause the electrons to move towards one side of the conductor. This can create a charge imbalance and a voltage difference across the conductor. This phenomenon is known as the Hall effect. Thirdly, it can affect the conductivity of a conductor. If a magnetic field is applied to a conductor, the Lorentz force can cause the electrons to move in a direction that is not parallel to the electric field. This can reduce the effective conductivity of the conductor. The effect of a magnetic field on the conductivity of a conductor is known as magnetoresistance. In summary, the magnetic field can exert a force on moving electrons, which can cause them to move in curved paths, accumulate on the surface of a conductor, and affect the conductivity of the conductor.